All right, so we're going to be solving the following questions on movement in the topic equilibrium of forces. So please pay attention. First question goes like this. A meter rule AB is pivoted at its midpoint C if a load of mass 2 kg is hung at a point 20 cm from C. Just reading it, it sounds confusing, I know. And that's why I encourage you, when you're solving a physics question that involves illustration, it's just best you sketch a diagram so it can be easy. So here I'm just going to draw a representation of a meter rule. Note that a meter rule is 100 cm long or 1 meter long, especially the ones used in the laboratory. So let's continue. A meter rule is AB. Okay, a meter rule AB is pivoted at midpoint C. So let's call the meter rule AB. At midpoint, so somewhere down the middle, this is midpoint C. And at midpoint, that's going to be at the 50 cm mark, because remember what I told you, a meter rule is 100 cm long. So at the middle is going to be 50 cm. Now, if a load mass 2 kg is hung at a point 20 cm away from C, okay, so let's draw the mass. So the mass will be hanging from the 30 cm mark, because it said 20 cm away from C. So 20 cm away from the pivot that is from C. As you can see, 30 plus 20, 50, right? 50 minus 30 gives us the distance between 30 cm mark and the 50 cm mark. So where should we hang a 1.5 kg mass to balance this meter rule horizontally? Definitely, these 2 kg will be pulling on this side of the meter rule. So we have to add a mass on this side in order to balance it. So they say, what should we add? A 1.5 kg mass. We don't know the distance from the center. We don't know the distance from the midpoint. So let's just call it x. Now, from our principle of movement, clockwise moment is equals to anticlockwise moment for meter rule in equilibrium, for a beam in equilibrium, for moment in equilibrium. That's principle of moment, right? So for this to balance horizontally, the clockwise moment has to equal the anticlockwise moment. Now, for the clockwise moment, we have 1.5 kg times its perpendicular distance, that is from the midpoint. So 1.5 times x is equals to anticlockwise. So this is anticlockwise direction, 2 kg times 20. Therefore, our x equals to 2 times 20 is 40, so just represent it 40 divided 1.5. And if we simplify further, we'll find that our answer is approximately, just press your calculator to get it. You can just press your JAMB calculator and you're going to get 26.67. Oh, I can already see an option that has 26.7. So 26.7 is the correct answer. This distance from point C, 26.7 cm away from C, is the correct answer. Or we can say 26.7, subtract it from 50 minus 26.7, or we can say 23.3 cm away from point B, or as we have it, 26.67 cm or 26.7 cm away from point C. That's the correct answer. Question 2. Masses M1 and M2. As usual, you have to sketch a diagram if you want to understand it easily. So I'm drawing what looks like a meter rule, a representation of a meter rule. Masses M1 and M2 at 20 cm and 65 cm mark respectively. So I'm going to gauge that this is around 20 cm mark. I'm going to call M1, and then we have 65 cm mark. So I'm going to gauge 65 cm is going to be around here. It is not to scale, it is just an illustration. So 65 cm. So this is 0 cm mark, this is 100 cm, and the midpoint, which is 50 cm, if it is freely suspended at its center of gravity, the center of gravity of a uniform meter rule is at the 50 cm mark. So I'm going to suspend it on a fulcrum or a knife edge or a pivot at 50 cm. Now they're asking us if the meter rule balances horizontally, determine the ratio of M2 and M1. Now this is 20 cm mark. The distance between M1 and the center is going to be what? 50 minus 20, that is 30. The distance between M2 and the fulcrum is going to be what? 65 minus 50, and that is 15. Right? So clockwise moment equals anti-clockwise moment. Clockwise moment is equals to anti-clockwise moment. So M2 times 15 is equals to M1 times 30. Now we can divide both sides by M1 because they're asking us for the ratio of M2 to M1. So we need to write M2 over M1. So we can actually divide both sides by M1. M1 cancels out, and then we can divide both sides by 15 as well to remove 15 from this side. We have to divide it by 15 as well. So we're going to end up with M2 all over M1 is equals to 30 over 15, which is equals to 2 over 1. And that gives us what? 2 ratio 1. So the ratio of M2 to M1 is 2 to 1. And so A is the correct answer. Number 3. A meter is found to balance horizontally at the 48 cm mark. Now we are dealing with a meter rule that balances at 48 cm mark. That means it's not a uniform meter rule. Uniform meter rule will balance at 50 cm, obviously. So what a uniform meter rule means is that its mass is evenly distributed across the length of the meter rule. But in this case, it is not. So I'm going to represent a meter rule. We already know that the balance point is at 48 cm. The balance point means that the mass of the meter rule will act along 48 cm mark. So I'm going to guess that this point is 48 cm, and this is the line at which the mass of the meter rule is going to act at 48 cm. Now, when a body of mass 60 gram is suspended at 6 cm, so somewhere around here, a body of mass 60 gram was suspended 6 cm. The balance point is found to be at 30 cm mark. So at 30, the meter rule balances horizontally. Then what? Calculate the mass of the meter rule. Okay, this is very easy. Calculate the mass of the meter rule. That is the mass M, right? So clockwise moment equals anti-clockwise moment. So distance from here to here is what? 48 minus 30 is going to give us 18. Distance from the 60 gram mass to the fulcrum is what? 30 minus 6 is going to give us 24. So if we take clockwise moment, M times 18 is equals to anti-clockwise moment, 60 times 24 Then make m subjects, divide both sides by 18. You're going to have 60 times 24 over 18. And we can just simplify by dividing by 2 until we reach a simple form. 2 here, 30. 3 can go into 9, we have 3. 3 can go into 30, we're going to have 10 left. Then what? 3 into 3, 1. 3 can go into 24, we're going to have 8, because 8 times 3 is 24. So I left with what? 10 times 8, this is going to be because 80 gram. So now we know that the mass is 80 gram. Okay, so we finally got to the mass of the meter row. So the mass of the meter row is what? 80 gram. Now, distance of the balance point from the zero end, if the body were moved. Okay, so if you calculate the distance of the balance point from the zero end if the body were moved to 13 cm mark. Now, there are two changes. Number one, if we move this body, 60 gram is the body that I'm referring to. If we move it to 13 cm mark, which is somewhere around here, then what is going to be the new balance point such that the meter row will balance horizontally? For that, we have to sketch another diagram with those changes. But the only difference now is we know the mass of the meter row. We have already calculated the mass of the meter row, so we already know the mass of the meter row. Now we're going to move the 60 gram to the 13 cm mark. So this is 60 gram, 13 cm mark. And then we don't know where the fulcrum is going to balance, right? But we are very sure that the mass of the meter row is 80 gram and it's acting at the 48 cm mark. So now there are two unknowns. We don't know the distance between the fulcrum and the 60 gram, so let's call it x. We don't know the distance between the fulcrum and the 80 gram mass, or that is the mass of the meter row, so let's call that y. Now clockwise moment goes at clockwise moment, right? So you can say 80 times y is equals to 60 times x. Well, we have two unknowns. We can simplify, we can just simplify, cancel 0, 2 here 3, 2 here 4. So 4y is equals to 3x. Now note something, that the distance here is 48 minus 13. So 48 minus 13, and we get the distance there. 48 minus 13, we have 35. So that distance is what? 35 cm. Therefore, x plus y is 35 cm. So we know that x plus y is equals to 35 cm. Now we have two equations. All we have to do is just make just solve simultaneously. This is just simple mathematics. God. Alright, so 35 minus y is the value for x, right? So we're going to substitute into this equation. So 4y is equals to what? 3 in brackets, this value for x, 35y. So just simplify for that. 4y is equals to 3 times 35 is what? 3 times 3 is 9, that is 90. 3 times 5 is 15. 90 plus 15 is 105. So 105 minus 3 times y is equals to what? 3y. Alright, so simplifying further, we're going to collect like terms. So we have 4y plus 3y is equals to 105. 7y is equals to 105. Divided by 7, we're going to get 35. Sorry, we're going to get 15. 15. So the value for y is 15. Therefore, the value for x is going to be 20. Because 20 plus 15 is 35. So let's go back to the question. What did they even ask us for exactly? They said the distance of the balance point from the zero end if the body were moved to the 13 cm mark. Okay, and that's exactly what we've done. The body was moved to the 13 cm mark, and the new distance of the balance point, the new distance of the balance point from the zero end is going to be what? 13 plus 20. So that's going to be 33 cm. Therefore 33 cm is the answer. And for question number 4, a uniform half meter rule. Note the word they use here, half meter rule. A meter rule is 1 meters or 100 cm. A half meter rule is going to be, as the word implies, half. So 50 cm or 0.5 meters. So let's sketch our diagram for the meter rule. So the meter rule is pivoted at 20 cm mark. Zero to 50, because it's a half meter rule, right? So because it's a half meter rule, we have 0 to 50 cm. Then the midpoint is going to be 25. It's pivoted at a point 20 cm from A. So this is our A and this is our B end. At a point 20 cm from A is going to be somewhere around here. I'm just estimating. So it is pivoted at 20 cm. If it is balanced horizontally by placing a mass 35 gram at A, so exactly at the 0 mark, a mass of 35 gram is placed. Calculate the mass of the rod. So the mass of a body acts along its center of gravity, and the center of gravity of a uniform half meter rule is going to be at the 25 cm mark. So we're looking for this mass M. Clockwise moment is equal to anti-clockwise moment. Taking the clockwise moment here, the distance between mass M and the fulcrum is 25 minus 20, that is 5 cm, right? So we have M times 5 is equals to anti-clockwise. So anti-clockwise, the distance 0 to 20, so 35 times 20. 0 minus 20. 20 minus 0 is 0. 20 minus 0 is 20 cm. That's why we have this here. So simplifying, divide both sides by 5. So we're going to have 35 for 20, divide by 5. 5 here 1, 5 here 4. 35 times 4 is 140. So the mass of the meter is going to be 140 gram. And finally, the last question. A uniform meter rule is pivoted at its center. loads of 15 Newton and 20 Newton are placed at 10 cm and 20 cm mark respectively. First thing you do as usual is to draw a representation of your meter rule. That's what I'm going to do again. I'm going to draw something that looks somewhat okay. So uniform meter rule at its center. Since it's a uniform meter rule, not a uniform half meter rule, 100 cm is going to be the extreme end, 0 cm at the extreme end towards the left, and at the midpoint where it is pivoted at its center, it's going to be 50 cm. So I'm going to pivot here, 50 cm. Loads of 15 Newton and 20 Newton are placed at 10 cm and 20 cm marks respectively. So when I say respectively, it means 15, let me use a color complex. 15 Newton was placed at 10 cm and 20 Newton was placed at 20 cm mark. That's what it means. So we're going to do that. So at 15 at 10 cm mark, 15 Newton force was placed, and then at 20 cm mark, Newton was placed. Then if the meter is balanced horizontally by a load of 40 Newton placed on the other side, so 40 Newton is going to balance the load on this side. Calculate the distance of the 40 Newton load from the pivot. Now we don't know the distance of the 40 Newton load from the pivot, so I'm just going to call it Y, because why not? So 20 Newton, the distance of the 20 Newton force from the pivot is what? 50 minus 20 is what? 50 minus 20 is 30. So the distance is 30 cm for the 20 Newton force. For the 15 Newton, it is what? 50 minus 10, which is 40. Now note, we are not using the distance here, because the distance here is what? 10 cm. But rather, the moment for the 15 Newton force is going to be span the entire length to the fulcrum. Don't ever make that mistake, because students make that error. It is 40 cm from the fulcrum, the full length. That's what you are using to take a moment about the pivot. Okay, so how do we go about this? Sum of clockwise moment is equals to sum of anti-clockwise moments. The only clockwise moment you see here is this one, 40 times y, 40y is equals to anti-clockwise moments. So we have 20 Newton times what? Times 30 cm. It's 30 cm from the pivot, because 50 minus 20 is 30, right? So 20 times 30 cm plus 15 Newton times what? Not times 10 cm, times 40 cm, the distance from the pivot. 15 times 40, so 40y. 20 times 30 is what? 2 times 3 is 6, so this is 600. 15 times 40. What about 15 times 40? 15 times 40, I'm going to leave 5 aside. 10 times 40 is 400. 400 times 5 is what? 400 times 5 is 2000. So we have 2000. This thing I'm doing is just how you can easily solve without always pressing calculator and wasting your time in doing JAMB. There are some things you should be able to solve with your head. So I added 2000 to 600, that is 26. Then divide both sides by 40, and we arrive here. So 26 divide 40, 0 cancels 0. We can even start. Okay, so 2 into 4 is 2. 2 into 26, we have 13. So 13 over 2. 13 over 2. Are you sure we're on the right track? Don't tell me I made that. Don't tell me I made a mistake. No, 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 no. 15 times 40 is what? Jesus. Jesus Christ. 15 times 40 is 600. Wait. 15. Oh my god. Oh my god. Oh my god. Casted stuff. Alright, so 40y is equals to 20 times 30. 2 times 3 is 6. So 20 times 30 is 600. Because 1 and 2 0. Right? So plus 15 times 40 is okay, so let's just split 15 into 10 plus 5, right? uh yeah, I have no idea what I'm doing. 15 times 40 is 600. 15 times 40 is 600. The reason I'm doing this so you can like quickly solve without a calculator in JAMB, so you don't waste your time always pressing calculator. But anyway, to be accurate, just press your calculator in peace, please. 40y is equals to 1 2, y is equals to 1200 over 40. 0 cancel 0. 120 divided by 4 is what? 4 divided 12, 3. So we have 30. 30 cm. That's our final answer. Back to this case, how did I figure out 15 times 40 is 600? Now, it's just simple. Should I call it simple? Anyways, it is easier to multiply 10 by 40. So 10 plus 5 is same thing as 15, right? So times 40. 40 times 10 is 400. 40 times 5, 4 times 5 is 20, so that's 200. 400 plus 200 is what now gives me 600. Let's just say hack to calculate with a calculator. And to wrap it up, I'm going to conclude with remarks and conclusion. Now, well, we not treat a case where you have a suspended meter rule. Sometimes a meter rule can be suspended from the ceiling at a point. Now, you may see some forces acting upwards, some forces acting downwards at varying distances from the fulcrum or from the pivot or the turning point. Now, one thing to note is the same principle applies no matter the case. Clockwise movements, sum of clockwise movements always going to be sum of anti-clockwise movements. Now take a look at this. If you want to take the moment about this point, how are we going to take the moment? First of all, you have to consider which of these forces, let's say we have force A, force B, and force C. Which of these forces are clockwise and which are anti-clockwise? It is very easy to know. This force is tending to turn the meter rule to this side, turning towards the left, right? It is anti-clockwise. So C is anti-clockwise. A is still turning towards the left, so A is also anti-clockwise. The only clockwise force we have here is B. right? So when you see a case like this, you still take moments about the fixed, not fixed, about the pivot from varying distances between the applied forces and the perpendicular force and the distance from the pivot. So clockwise movement is still always going to be equal to anti-clockwise movement if this meter is to balance horizontally on this pivot. And finally, there is a rule that the sum of upward forces have to be equal to the sum of downward forces. So in this illustration, the upward forces are what? C. And the downward forces are what? A and B. They're acting downward. Only C is acting upward. So by that rule, we can say that force A plus force B has to be equal to what? Force C. This is just an example. Now if there was another upward force D, then A plus B is going to be equal to A plus C plus D. That's just the concept. If you have any questions.